motion in a plane. During the last videos, we have been working on motion in one dimension. Today, we are going to see motions that do not only go along the x or y or z axis, but in a plane. For instance, this hatched place is a xy plane. This one ticked good is YZ plane, whereas this one is a ZX plane. So for instance, if a motion is this way, let's say this way, you see that there will be Z component and S component here. If it is here, there will be Z component here and S component there. If it is moving this way, let's say this way, there will be Y component here, which is here, and S component here. Here and here are the same. Here and here are the same. So also here and here are the same. Here and this point are the same. If it's on this plane and it's moving this way, there will be the component here and the component here. So we want to now decouple the equations of motion that we have obtained. For instance, V is equal to V naught plus AT. V is a final velocity, V naught is initial velocity, and A is acceleration. So of course you know how to write this in component form. Vxi plus Vyj is equal to V naught xi plus V naught yj plus A is ax plus ayj hat times time. So that if we open this thing up and they take like terms both on the left hand side and on the right hand side, we will get that Vx for I components, Vx is equal to V naught x plus ax t is a ith component, while the jth component, you take the j, it will be V naught y plus ay t because it's multiplying. So this is the first equation for this first Newton's equation. So for the second one, let's use the formula R, that's position vector is equal to the initial position vector, which we can assume to be 0, plus V naught t plus half at squared. So if we open it up, we have x naught I plus y naught j hat for this one, plus V naught x I plus V naught y j hat into, you close the bracket, times time plus half ax I hat plus ay j hat t squared. So we can choose the components immediately. That's collecting like terms of I. Remember, on this left hand side we just have x I hat plus y j hat. If we open it up, so that if we collect like terms for I, the components of I, will have that x is equal to x naught plus V naught x times time plus half ax I t squared. This is the ith component, while the y component, the z component, will give us the displacement along the y-axis, which is y naught, this one, plus V naught y v naught y times time plus half ay t squared. So that is the second one for that. Let's use the third equation, which is v squared is equal to v naught squared plus 2a times position vector final minus position vector initial. So we have on the left hand side, what we will have is a vx squared I hat plus v squared j hat squared is equal to v naught x squared I hat plus v naught y squared j hat for this one, while this one is for this one. Then plus 2ax I hat plus ayj hat into x I hat plus yj hat minus x naught I hat plus y naught j hat. So there's a square bracket here to distinguish, so that we obtain if we choose them component wise. If we choose it component wise, we will have that vx squared is equal to, for the ith component, is equal to v naught x squared plus 2ax 2ax into x minus x naught, So also if we write for the j component, which is y squared is equal to v naught y squared plus 2ay into y minus y naught. So this is the third equation. We can also do for the last one, r vector is equal to the average velocity initial plus final times time, so that they have that x I hat plus y j hat is equal to half into v naught x I hat plus v naught y j hat plus, for this one, that's what I have done, plus vx I hat plus vy j hat plus vy j hat, so that if we take the component forms of for I, we have the x is equal to half v naught x plus vx times time, that's t here, times time, and y is equal to half v naught y plus vy times time. So in all this, we decouple this term. There are two independent motion, one for y and one for z. When you are solving it, you try to, since it's vector, decouple the vector in two component forms.